Good morning. This is Nick DeMott with my MedChem honors project. Today we'll be talking about monoamine oxidase B, or MAOB. Monoamine oxidase B is essential in the human body for deaminizing several key compounds. It is involved in the deamination of dopamine and is responsible for the metabolism of several key neurotransmitters. It does this through a FAD cofactor, and the enzyme is bound to the outer mitochondrial membrane. This enzyme is of significant medical concern due to its association with several neurological disorders such as Parkinson's disease and Alzheimer's. It is known to be inhibited irreversibly by a molecule known as L-deprenyl. To understand the mechanism of action of monoamine oxidase B, we can take a look at how a typical amine compound would bind to the FAD coenzyme. Here we see that the lone pair on the amine will bind to the activated carbon on the amine group on FAD. Once it is bound, the mechanism begins acting on the amine, and the first step of this process results in an imine. Monoamine oxidase B can be inhibited by a molecule called deprenyl. Deprenyl binds covalently and irreversibly to the FAD coenzyme, stopping it from being able to deaminate amines. Deprenyl has been used to some extent to treat Parkinson's disease, although it has some side effects and there is room for improvement. Here is a three-dimensional visualization of FAD bound to deprenyl, also showing interactions with some key amino acid residues on monoamine oxidase B. Here are these interactions visualized in 2 dimensions. We can see that quite possibly the most essential amino acid residue for binding deprenyl to the enzyme and to the coenzyme is tyrosine 60. We can see that there are probably some strong van der Waals interactions between the aromatic ring on tyrosine 60 and the iaromatic ring on deprenyl. The majority of our focus on enhancing the activity of deprenyl should be targeted towards enhancing these van der Waals interactions. Let's talk about some potential modifications we can make to L-deprenyl. First, let's take a look at its structure unbound to FAD. We see that there is a tyrosine ring attached to 2 carbons. This section of the molecule is most likely essential for binding to monoamine oxidase B and to the FAD coenzyme. It is possible we could enhance the binding interactions here by methylating, lengthening the chain, performing some ring closures, or possibly shortening the chain if lengthening the chain causes too much steric hindrance. The amine group is likely essential for the stability of the molecule, or it possibly mimics a natural enzyme, a natural substrate that would bind to the enzyme. This may allow it to effectively enter the active site of the enzyme and to bind to FAD. The one part of the molecule we don't want to touch here is the alkyne at the end. This alkyne is what binds to the nitrogen on FAD, and removing this alkyne would likely drop the activity of the enzyme significantly. Thank you for taking the time to watch this presentation, and thank you to all these wonderful researchers who have allowed me to read their research and get to learn about this wonderful enzyme. Thanks.